says represents Progress Carticon, and we used to have Mike Parrish, who is retired, and it's really nice to see new generation of experts replacing old warriors, and Seth is one of them, as I understand. Seth recently presented at the monthly decision session, and it was quite nice presentation about decision table compressions. This is a feature included inside the latest Carticon version. Also, Carticon provides quite interesting test generation facilities that sometimes they can address even optimization problems, and you can check set solutions on DM community challenges. So Seth is really becomes quite active in this area, and I'm happy to welcome him to DecisionCamp.
Thank you very much, Jacob. Should I get started here?
Yeah.
Sounds good. All right. Good morning, afternoon, evening, everybody. As Jacob mentioned, my name is Seth Meldon. Really appreciate the opportunity. And as coming out of the last presentation, which was pretty technical and very interesting to learn about, I'm kind of going to be speaking a bit on the other end of the spectrum about more conceptual and just more value-based things of the concept of transparency and what I think is especially useful to work towards in the field of declarative AI overall. In the spirit of full disclosure, as Jacob mentioned, I work for a company called Progress. My work centers around building solutions with the business rules engine Corticon. And I doubt it's necessary to describe this too much for the audience, but business rules engines, for those unfamiliar, are just one framework for essentially maximizing the extent to which automated decision-making logic can be implemented by individuals with the utmost familiarity in the actual decision being made, as contrasted with implementing that decision in application code. For example, a financial analyst taking a larger role in the implementation of financial portfolio management automation, as opposed to simply describing the ideal implementation to a separate team of application coders. Now, that's certainly valuable to the companies that implement those solutions. These solutions often pay for themselves through shortened change cycles, improved documentation, agility for business change, shorter onboarding time of knowledge workers. So in a variety of ways and across many different contexts, declarative logic with rules engines provides for far greater, really, democratization of the implementation of automated decision-making logic. And I'm not going to talk too much about Corticon today, but that's really something that has developed as far as why I'm so passionate about the field is conceptually the value derived from enabling a variety of users, not merely the business analyst, not merely the IT department, but as many cross-functional implementers to have a hand in the implementation of any given complex decision. It's not just useful and it's not just profitable and provides a measurable ROI for the business, but it likewise serves to benefit essentially the population by really allowing for a greater degree of difference in perspectives in the actual implementation of decision-making logic, which obviously can affect large groups of populations. So that's what I'm really looking to focus on today, the limits of usefulness in cutting-edge AI as qualified maybe from a random sampling of humans on planet Earth, because maybe that financial portfolio manager analyst make up a company that's not existing today, say, maybe they work for Lehman Brothers, maybe they work for Enron. So what are the sort of limits of decision-making that we might want to consider as far as exceeding what we might find useful beyond just the realm of implementing complex logic, but how useful in general is a complex set of logic for decision-making. So with that bit of context set, I'd like to kick off by just grounding the discussion a bit with a few perspectives of some of the leading contemporary voices in AI research within academia who I look to in this area. Second, I'd like to talk a bit about some of the other areas of scientific research historically that provide some pretty invaluable lessons to technologists innovating in this field of declarative AI, in my opinion. And finally, I'd like to present a case study or two of a few corporate innovations that kind of exemplify automated decision-making that have kind of gone above and beyond past the limits of usefulness as we might want to define it in the field of declarative AI generally. So getting started, just thinking ahead in terms of on human machine objective alignment. And that phrasing is something that I found pretty valuable from a gentleman named Stuart Russell, who is an author of a book called Human Compatible AI. He's a computer scientist known pretty well for his contributions to AI. He's a professor of comp sci at University of California, Berkeley. He's an adjunct professor of neurological surgery at University of California, San Francisco. So I was watching a recent video at a conference called AI and Law. And one thing that he really honed in on, and something that he talks about a bit in his book, is a bit of kind of reformulating what the end goal is in terms of AI and AI research, because as he says, in its present form, it really studies the ability to achieve objectives, not necessarily the design of those objectives. And that problem, in order to reclassify it and essentially make sure that our AI innovations are really human compatible, as he defines, requires a redefinition of AI itself from a field concerned with the unary notion of intelligence as the optimization of a given objective to a field concerned with a binary notion of machines that are provably beneficial to humans or not. So that's what I'd like to focus on a bit today. Machines that are provably useful, provably beneficial to humans. What I consider and what I'd like to classify today as the limits of usefulness, because there's a broader context besides just the given use case that we're implementing as practitioners here. For example, a limit of usefulness, there might be a extremely effective self-operating napkin. For a variety of reasons, we might not find that a useful implementation of a given set of technologies. It's not a particularly useful innovation in general. Just to set some, what I think are some valuable historical events that really introduce some main influences, to me at least, for this field and this general discussion. What I want to start by just talking a little bit about is not just the concept of interoperability, which is certainly familiar to a lot of this audience, but more specifically adversarial interoperability, which essentially means not just the ability for a given technology to be interoperable with the next technology, but for competing firms to have the ability to build upon and innovate from existing technologies. So as one illustration of this, something I like to talk a little bit about here is back in 1904, in what was really over a one-day stretch, it took 30 hours over the course of a couple days in February 1904, when more than 1,500 buildings were flattened by a fire in the US city of Baltimore, Maryland. Baltimore firefighters were assisted by units from Washington, D.C., Philadelphia, Wilmington, Delaware, even New York City. They weren't particularly helpful, these reinforcements, though. Really, they only came to watch. The problem was they had fire hoses which did not fit the couplings of the hydrants for those outside of the U.S. Obviously, the fire extinguishing infrastructure here is lots of different fire hydrants, which firemen will use to put out fires. At that time, there were over 600 variations of fire hose couplings. So no city, obviously, having already made that investment, wanted to abandon their investments in the current infrastructure manufacturers would patent their couplings to prevent competition, and the differences in diameters and threads protected those incumbents from competition. And obviously, at the same time, this can make it difficult or impossible for communities to assist each other, which of course would threaten property damage and loss of life. So that's exactly what happened here. And it's kind of the worst case scenario as far as disaster striking in the absence of adequate regulation, and that being the catalyst for the standardization of hydrant fittings. But what we're going to talk about a little bit further and hopefully discuss a bit more is this story really takes a variety of shapes. For example, take printer manufacturers that in a series of cases in the 1990s here in the US, there were many cases with the Supreme Court around whether or not they should be allowed to essentially hold consumers captive to the original manufactured printer by only allowing printers to be refilled with ink from that original manufacturer. Ultimately, the US Supreme Court decided, no, that's not very useful in a general market competition framework. Similarly, what you see in many cases today with car manufacturers that might limit third-party repair facilities from the ability to address any repairs for a given car model. Now, there's a few more scholars that I think are useful to look to here. Norbert Wiener, who was a mathematician and philosopher, he earned his PhD from Harvard University at age 18 years old. So no slouch himself. A key achievement of his was inventing a mathematical theory of feedback in biological and engineered systems. And that helped clarify the concept that intelligence is the process of receiving and processing information to achieve goals. So he's considered by many to be one of the founders of modern AI as we consider it today. He wrote once in a paper called Some Moral and Technical Consequences of Automation that was in Science magazine all the way back in 1960, that though machines are theoretically subject to human criticism, such criticism may be ineffective until long after it's relevant. So to be effective in warding off disastrous consequences, our understanding of our man-made machines should develop pari passu, or at the same rate, with the performance of that machine. Otherwise, by the time we react to the information conveyed by our senses and actually try to stop the car we're driving, it may have already run into the wall. So that's 1960. And obviously, again, same story, different characters involved, different series of events. Fast forward to today, again, myriad illustrations. This was probably familiar to a lot of this audience. But back a few years back, I think it was 2016 or so, Microsoft's Tay chatbot, as a frame of reference, was Microsoft's experimental teen Twitter chatbot. It used machine learning to mimic the Twitter habits and conversational tics of teenagers and young adults. And having learned from Twitter as its data set, you might not be surprised to know that within one day, Tay had her plug pulled. She's never brought back online because she had machine learned her way into learning to tweet remarkably offensive content. We're talking stuff about Nazis, about things that would really offend just about any particular audience imaginable. That's how long it took for Tay to learn to offend that widest scope of humans. So even in 2016, we hadn't necessarily learned so much of our lesson, but there's some more that we can, that doesn't have to be the case. I'd like to consider a scenario from a field of innovation that is almost as well, that is even more of a focus in the US than AI, back in the time of speaking about biochemistry and the concept of critical human review, not catching up to the car that we're driving. So scientists knew as early as the 19th century that DNA was one of the most basic molecules of life. It carries genetic instructions for the development, the functioning, and production of all known living organisms. But it wasn't until 1950 that scientists discovered the actual basic structure of DNA, that classic double helix shape that we all picture and learned about in school. Many scientists had a hand in its discovery, but scientists named Watson and Crick were the were the first to publish it in the journal called Nature. This is a snapshot of their actual journal article, where the model proposed not only clarified the helix shape, but that shape itself answered a few more questions about genetics, namely how DNA makes copies or replicates itself. It essentially implied that DNA delivered the instructions for copying a new organism by separating those two strands of the helix, which are then used as a template for copying the DNA. They noted something curious, a bit of an understatement, a bit amusing. It's not escaped their notice that the specific pairing that they've postulated immediately suggests a possible copying mechanism for the genetic material. That is, as we might think of it in the Dr. Evil sense of the word, some real cloning potential is where this initially comes in. And so obviously back in the 1950s, there's really no basis and no frame of reference for the ethical side of cloning, how to approach the research and development of it, and what parties should have a say in developing the regulations and just the frame of references for how we approach the actual development of those types of technologies. So in 1971, a Stanford biochemist who's considered the father of genetic engineering, he was named Paul Berg, or is named Paul Berg, he's still with us. He began planning an experiment to introduce tumor virus genes into a mammalian cell in order to determine whether it could become part of that cell's genetic makeup. And that process, called recombinant DNA or rDNA technology, essentially the joining together of DNA molecules from two different species in order to insert that recombinant DNA into a host organism to produce new genetic combinations. That was the focus of a lot of his research. Specifically, in 1971, he was looking at doing an experiment where, in essence, he would be splicing together a monkey virus, a simian virus called SV40, and a bacterial virus or a bacteriophage, and taking that E. coli or the bacteriophage and inserting the SV40 directly into it. Now, while working on that project, Berg's colleagues raised some potential concerns that the experiment might produce an organism that could carry cancer genes with the potential ability to spread epidemics of cancer. Thinking back a little bit to Norbert Weiner's quote, "By the time we react to the information conveyed by our senses and stop the car we are driving, it may have already ran head on into a wall." Not a direct quote, but one of Paul Berg's students made a point of catching this and essentially asking the question, if this kind of genetically engineered organism were to escape from the lab, could it infect people and increase their chances of developing cancer? Well, the experiment was ultimately postponed indefinitely, and they self-imposed a moratorium on this rDNA experiment. And in order to really get a better grasp on how they should approach this sort of research, they began planning for a conference to discuss with a broader scientific community the dangers inherent and precautions necessary for this sort of research. They organized a series of different conferences in the 1970s in Asilomar, California, called the Asilomar Conferences on Recombinant DNA. Importantly, something I want to highlight is they invited a lot of different walks of life as far as the participants in attendance. Lawyers, journalists, and government officials were there, not just biochemists. And ultimately, the members of the conference decided to place a moratorium on two phases of rDNA research. First, they stopped the introduction of antibiotic-resistant genes or bacterial toxin genes into the bacteria. Second, they stopped the introduction of DNA from tumor viruses or any other animal viruses into reproducing DNA organisms. Those restrictions that they developed on gene splicing as proposed at the Asilomar conference by the scientists practicing these techniques, as shown here in this snapshot, those are still the basis for regulations and laws for many countries, not just the US, under which gene splicing here in the US would recommence in 1976. It's continued to be the subject of a lot of different controversy, but importantly, it has been the subject of controversy. There has been free debate amongst various practitioners, not merely just the biochemists who have the intimate familiarity with the rDNA technology. Looking back on that series of events, Paul Berg spoke about a bit of retrospective, and this has been something of a highlight for AI researchers today, talking about the lesson he derived from Asilomar for all of science, that the best way to respond to concerns created by emerging knowledge or early stage technologies is for scientists from publicly funded institutions to find common cause with the wider public about the best way to regulate as early as possible. When scientists from corporations are the ones dominating the research enterprise, it'll simply be too late. So let's talk about a few examples that have some serious parallels with that story, but let's talk 2021. For an example, in this regard, I'd like to give a little bit of background into something that some may have no experience at all in the realm of medical diagnosis coding. So in terms of just the ICD-10 coding and how clinicians actually code medical diagnoses, when you have a sore throat, that's called a symptom. If that sore throat lasts more than a day or two, you probably visit the doctor, get his or her opinion about the cause of that sore throat. And then based off that symptom, the sore throat, maybe an exam of your physical condition, the doctor may arrive at a diagnosis. But more than 100 diagnoses could possibly be the cause of your sore throat. So how is the doctor going to arrive at the correct diagnosis? Well, they review things like historic symptoms, hereditary or environmental past, family and social history. And once all of this is documented in words by the doctor, they're able to convert this into a diagnosis code number. Now, the ICD-10, revision 10, clinical modification, I'll just call it ICD-10. It's used in the US for diagnosis coding, but in most of the world as well. And it contains over 71,000 unique codes. This does not mean that each of the more than 100,000 known disease entities has a separate code. When the phrase diagnosis code is used, its actual meaning is really diagnosis category code. An example of a diagnosis category could be R79.0, which refers to an abnormal level of blood mineral. So a diagnosis code category is analogous to a zip code in the US in that way. So New York City has 145 zip codes. Other cities, or excuse me, other states have more than one zip code, or only one zip code to represent multiple cities. So just with the zip code number, it's not possible to positively identify which town we're talking about. Now, there's a lot that can go wrong that is a bit cliche to talk about things like the handwriting of a clinician or in writing some notes, some of the challenges that might come from voice transcription of notes from a clinician visit. But there's no shortage of ways that errors can be logged accidentally into a health record system, the software that a doctor is using for a given checkup. And these really run the gamut of different types of things. So talking again about things like handwriting or physician diagnosis that's just not really logical to look through, things like a fractured earlobe, which isn't anatomically possible. Things that are merely an issue with the voice recognition software they're using. Liver birth, for example, might be live birth, and so on. There's a lot of things that can go wrong, and a lot of them are pretty well known to most of the audience, especially when maybe they've tried to read a doctor's note in the past. Now, I'd like to talk even more specifically about a particular type of diagnosis called sepsis. For those unfamiliar, sepsis is a really life-threatening organ dysfunction caused when an infection that you already have, it triggers a chain reaction throughout your body. The body's response to the initial infection begins to damage its own organs. And as you can see there, the mortality increases are pretty remarkable, almost 8% for every hour after that initial onset of low blood pressure within those cases that have been positively identified as sepsis. And it's a pretty straightforward way to treat it involving antibiotics, but it's not a straightforward way at all to know at what point you can positively identify that diagnosis as sepsis. Given all these different potential variables involved, automated sepsis warnings within an electronic medical record system that the doctor is using in order to warn them of the potential onset of sepsis have huge potential. It's a huge area of investment in clinical decision support systems and rules engine softwares in general, because there's lots of different key symptoms that this condition, such as low blood pressure or any of these others, might represent as far as things that are likely indicators of the onset of sepsis. And sepsis is a frequent common pathway to death. It's never the initial reason you go to the hospital, but it might be the reason that an individual doesn't leave alive from that hospital. A recent scientific publication estimated that in 2017, there were almost 49 million cases and 11 million sepsis-related deaths worldwide. So that's almost 20% of global deaths in 2017 alone. It's highly correlated with a few of the fatal aspects of COVID-19. Not going to focus on that today. Even in 2017, though, almost 20% of deaths. Now, there's a lot of challenges that go into this. Sepsis, by virtue of the fact that it's never the initial diagnosis, it's always a resulting identified medical condition resulting from a variety of different infections. It can have so many different causes. It can have causes related to trauma, to burns, adrenal insufficiency, to heart attacks, aneurysms, drug overdose. And each of those potential causes has a variable time of onset a variable time of sepsis onset. So it's very hard to make any concrete deductions based upon what an individual's initial diagnosis is and when that might lead to a potential sepsis onset. Nonetheless, being able to collect some data, especially in the form of medical codes, that can at least allow us to derive some sort of insights, some sort of statistical likelihood of the onset of sepsis, regardless of the identification of the initial infection, is tremendously valuable. Now, again, part of the problem with even identifying sepsis comes on the side of testing. So there's no test at all that can detect sepsis rapidly enough to be useful. By the time that it is identified, it's usually too late, and that means that it's much more a matter of clinician experience and knowledge to be able to identify sepsis positively. As I mentioned, there's a multitude of relevant tests that physicians can perform, and these vary actually country to country. So there are about 30 people on this call representing a variety of different countries. Each country has, depending on which country you live in, if there's an onset of sepsis, the health institutions in a given country have a wide variety of definitions of the tests that should be performed in the case of sepsis. But typically what they'll do is, based upon the risk factors that are identified, they will perform a risk stratification of if you're exhibiting X, Y, and Z symptom. If this specific test has shown this particular result, then however drastic it is, then we're going to triage you appropriately. But again, that can vary country to country with varying levels of adoption country to country. Now let's make it even more complicated. Sepsis has been the subject of a lot of research over the past 30 years alone, which means that in 1991, we had our initial international sepsis coalition, I believe it's called. They introduced their first definition of how to identify sepsis and what actually goes into it. It's been changed twice since then, the international sepsis definition used by the World Health Organization. And it's certainly not done being evolved. There's more concerns being raised off this sepsis 3 definition. So all that clinical decision support, business logic in rules engines, in electronic medical records through the form of application code, it means automating the detection of sepsis. It's quite difficult. So there's concerns today about the sepsis 3 definitions. And so it's really a moving target to even be able to derive any sort of historical insights, because that data has changed so much over time. We've had a different understanding over time of what goes into sepsis, the codes that make up a given sepsis diagnosis, and so on. So let's talk a little bit more about that coding side. And this is all going to relate back to how we can better identify as a population sepsis and treat it better at the onset of it. So in February 2020, the Journal of Thoracic Disease put out a publication that studied a bit about practitioners' ability to derive any sort of insight from past incidences of sepsis. And I think this is very important to hone in on and think about in the context of a wide variety of topic areas. Obviously, as practitioners, we have a variety of industries that we work with developing rules solutions, and all these different potential moving targets that go into defining potential future policy based upon past data. It takes a lot of things for granted. Our ability to derive insight from past data when things like the denominator is changing based off things like the estimates are being biased from increasing clinical awareness of when to look for something, more screening, decreasing diagnostic thresholds, diligent coding practices. There's, again, value in exploring machine learning algorithms that can assist clinicians in identifying and treating sepsis. But like with the experimentation of gene splicing, there are so many considerations that it would really be foolish to not take into account and to not invite a wide variety of stakeholders and perspectives into the development of such an algorithm. For example, things with the energy industry, the ability to develop policy based upon past changes that were developed, historical data that's been developed based upon oil drilling operations, and our ability to develop policy based off of that can always be flawed, because the Earth tends to be an entirely different Earth than at the time that data was initially collected, due to the evolving and expanding role that climate change has on the operations of that sort of drilling. So that gets me to a quick case study with by far the market leader in electronic medical records here in the US. They have a 2% footprint across the globe, but more than half of US patients, any patient that has their data in a medical record in the US, which is the scope of this research, has their data stored in Epic's EHR. Like a lot of other EHR technologies, Cerner being one of them, between the two of them, they dominate the EHR market. Both Cerner, Epic, and a few other EHRs offer an early warning system in their the software that is being used by those clinicians in the emergency room. And it's included as part of Epic's EHR and is used currently at hundreds of hospitals throughout the US alone. Now, the model was developed and validated based off Epic systems, based on data that they collected from 405,000 patient encounters across 3 different health systems across 3 years. Sounds like a great sample size, and it very well likely could be. And this is an example of there's certainly value to the organization that implements technologies that involve declarative AI, that make use of natural language through rules engines, such as the one I am most familiar with, Corticon. But it's only so useful if independent validators don't have the ability to validate the underlying algorithm and the actual data upon which the algorithm is based. So Epic tells its customers that its sepsis warning system can correctly distinguish 2 patients with or without sepsis at least 76% of the time. Now, you can either take their word for it, or you can become a customer. To become a customer means you can validate their data. Otherwise, it's not available to the public. That's a risky proposition for a variety of reasons. I'm not even going to necessarily talk about the macro implications and just the fact that more than half of the US population has their data within Epic EHR, and that's the basis The more than half of the US population, if there is going to be a sepsis automated warning system that is triggered based off their admission to the hospital, it's going to, again, be just based off of taking their word for it, that is going to be an accurate depiction of a likely sepsis case. Now, up until about 2021, June of this year, there had been no independent validations of it. I want to talk real quickly about what happened in June 2021, which was when Michigan Medicine, which is the medical school at the University of Michigan, they put the model to the test based off what they could derive from their internal data around sepsis diagnoses. Again, Michigan Medicine, being a medical school, has its own hospital that they run. They can derive their own anonymized data based off of the patient admissions. And so they studied data from 2018 to 2019, 30,000 patients, 40,000 hospitalizations, and they looked at the implementation guidelines that Epic provides for tuning their Epic sepsis model. And they first noted how often Epic's algorithm would actually flag people who developed sepsis as defined by the US Centers for Disease Control and Centers for Medicare and Medicaid Services. And they compared those alerts, their own data, they compared the alerts that system would have triggered with sepsis treatments that were actually logged by their staff, who did not see Epic sepsis alerts for patients that were included in the study. They found that the researchers at Michigan Medicine found that the Epic system wouldn't make a hospital much better at all about catching sepsis and could actually burden staff with the unnecessary alerts produced by the EHR. It didn't identify 2/3 of the roughly 2,500 sepsis cases in the Michigan data at the time. And even more importantly, again, there's the concept of alert fatigue that comes into play with electronic health records and clinical decision support systems built into them. Obviously, there's the concept of the boy who cries wolf just as much applies when it comes to alerts within a medical record. The 9th time, as in this case, there would be 88 out of 100 times when the Epic system produces an alert. For those 12 times that it was correct, there's going to be a degree of alert fatigue when the clinician's going to simply ignore and is probably going to be right about whether or not they should ignore that alert produced by the Epic sepsis model. Now, this was, I mean, again, I mentioned I'm not going to talk too much about the macro side, but there's quite a legitimate commercial side as well. Like this is just a quick snapshot I took of the major publications that highlighted on very high up on their headlines that this market leader in electronic medical records, by essentially mitigating the usefulness of electronic medical records that leverage declarative AI, it's essentially rendered useless if independent validation cannot be accessed by academia. So there's certainly a limit of usefulness that we can identify in this way as well, similar to what Paul Berg warned about back at the Asilomar conference in his retrospective. I take a few conclusions based off of this, and I think this is in part an illustration certainly of the value of rules engines and declarative AI, but there's a bit more that you need to commit to as far as ensuring the usefulness of declarative AI in general. Because number one, regulations almost by definition cannot be expected to keep pace with AI. So it really is reliant upon the broader population to consider the broader repercussions of AI implementations in any use case. Moreover, there's plenty of situations, especially when you consider the degree to which the US is far behind the EU in terms of data privacy laws, in terms of widespread cybersecurity regulation in general. It's not really useful necessarily to rely upon any particular power center to decide what is or is not beneficial AI. So I think essentially to conclude that the more beneficial formulation here of what is or is not beneficial AI, what surpasses the limits of usefulness, can simply be a measure of how democratic that AI is. The less democratic, meaning openly available and accessible, the process of ideation and implementation of AI in our everyday life, the less provably beneficial the AI can plausibly be. We have no means to prove that it's beneficial. We have no reason to assume that it is. Thank you.
That was great. Thank you, Seth. It's interesting. I did some work for a healthcare software provider probably almost 10 years ago, and sepsis was one of the things they were looking at. Now, they were using other methods, but I think they were kind of moving towards that type of idea that you could do this. But again, it was their secret sauce. They weren't going to tell anybody how they were doing it. And it's one thing if you are doing something that doesn't impact people's lives, but like you say, when this is something that is literally a matter of life and death, it would be for the greater good if they could share the methods and the decisions and so on that come from there.
Exactly.
Okay, so we can open it up for questions. If you have a question you want to ask yourself, you can put your hand up on Zoom and I'll call on you. Or if you want me to read out a question, you can just put it on the Slack channel and then I will read it to Seth. Oh, we have Bob Moore. Bob, would you like to go ahead?
Yeah, I think I'd just really like to say, I mean, it's very interesting what you've had to say, Seth, but I think the issue about being open is one which is a very general problem in medicine and pharmaceuticals at the moment. I mean, one of the things which is continually being sort of popping up with people discussing about the reproducibility of scientific results and so on is that there is a big tendency for people not to publish on what they think are uninteresting results. They're not interested in publishing failures, and all of that information is actually feeding into an understanding of what would actually be the right way of doing things. And so there's a huge amount of experimental work that's going on, as well as the sorts of statistics that we're gathering from patients, which is just never appearing. And openness, not only about if you built a system, how it's working, but also openness about other things that you have been doing which didn't quite work out the way you wanted them to, is a big hindrance in terms of actually as improving a lot of healthcare outcomes.
Definitely. Between that and the however unquantifiable number of types of these studies that are simply not pursued because there's some degree of overlap with studies that have already been done. Perhaps there's trademarked in some sense, or it's just not innovative enough to be deemed worth the time, between that which is not pursued and the data for studies, like you mentioned, that is not particularly fruitful. That's certainly is irrespective of whether or not those results would have been useful to the general public.
Okay, well, I think that's that question answered. If there's anybody else who has questions.
If we don't have any other questions, we can end this session a couple minutes early. And if you do have questions for Seth, you can put them on the Slack channel and he can take a look at them over there. I just put a note on the Slack channel. What I'm going to do is just share my screen briefly, because at this point,